so the divergence theorem. So the divergence theorem is a relationship for a vector value function between a surface integral and the divergence of the vector field with respect to the volume. Okay? And the divergence is the gradient dotted with the vector field. So it's the derivative of each component with respect to x, y, and z. Okay. So let's just start with an example. Okay. So let T be the solid. Bounded by x squared plus y squared is going to equal 4. And the planes z which equals 0 and z which equals 3. So what we're going to do is we're going to calculate the outward flux of a vector field x, y, and z, which equals x, y squared I plus y, now z squared j, and then plus z x squared n. Okay, so the first thing we need to do on this problem is we need to consider what is the solid that we're actually dealing with. And then what we need to do is actually calculate the divergence of this vector field. Okay? So, all right, now if we say we have a solid bounded by x squared plus y squared equals 4. Well, x squared plus y squared, which equals 4, is a circle just with the radius of 2. So if we have a circle in the xy plane with just a radius of 2, it's also going to be bounded by z which equals 0 and z which equals 3. A little bit of room. And so how would I describe this solid? So I have my x, my y, and my z. And so this is a circle with a radius of 2, so 1 and 2, and 1 and 2. Okay. And I'm going to make this the back part, so I'm going to use dotted lines. Okay. So if z which equals 0, I mean, when I'm talking about the plane z which equals 0, I'm within the xy plane. And then we're going to go up to 1, 2, and 3 to the plane where z would equal 3. Okay, so this will be the top part of my cylinder. Okay, so we have a plane with, we have a cylinder that starts at the plane z which equals 0, and goes up to the plane z, which equals 3. And it's a cylinder with a radius of 2. Okay? So this is going to be the domain that we're going to be integrating upon, because we're going to turn this surface integral into a three-dimensional integral. And so since we're dealing with a cylinder, you got to kind of think, we're going to do this in the cylindrical coordinate system. Okay? And so, remember, the cylindrical coordinate system is going to be, we're going to have a radius, which is going to go from 0 to 2. We're going to have a theta, which is going to be the rotation within the xy plane. Well, this is going to be a full cylinder, so this is going to go all the way from 0 to 2 pi. And then my z, well, if I'm talking about just going up in the z direction, my z is just going to go from 0 to 3. So we end up with a three-dimensional integral that's not going to be too complicated, because we won't have a bunch of different functions on the inside. So now we need to calculate the divergence of this thing. So the divergence of the vector field, okay, so this is going to be the partial derivative with respect to x of xy squared plus the partial derivative with respect to y of yz squared plus the partial derivative with respect to z of zx squared. Okay. So the partial derivative with respect to x of this guy would be y squared. Partial derivative of this with respect to y would be z squared. The partial derivative with respect to z of this guy would be x squared. Okay. So now we have the divergence of the vector field, and we have the region that we're going to be integrating upon. Okay? So let's do this triple integral within the cylindrical coordinate system. Okay, so we're going to go back to this formula. Okay, so we're going to do the triple integral of the divergence of f. And I'm going to reorder this a little bit, just so it says x squared plus y squared plus z squared. You normally like it that way. Okay, so let's move all that up right there. And so we're talking about the triple integral of t of the divergence of f dv. Okay. So that's going to be the triple integral on t. I'm going to rewrite this in just a slightly different form. Okay. And now, since we are talking about the cylinder, honestly, you see the x squared plus y squared plus z squared, and some people would say, well, why don't we go into spherical coordinate systems? Because we have x squared plus y squared plus z squared. The reason that we're not going into spherical coordinate systems is that our actual domain is a cylinder. So we want to transform into cylindrical coordinate systems. And so when I transform into cylindrical coordinate systems, x is going to equal r cosine of theta. Y is going to equal r sine of theta. Well, on z is just z. We don't mess with z. Okay. And also remember that according to the Jacobian, that dv Now, this is not unique in the ordering that I'm going to write this, but I'm going to write it like this. R, dr, dz, d theta. Okay. Now, the dr, the dz, the d theta, they can be reordered in different ways. But the main thing that you want to get out of this is that you have to include this extra r right here. And so that r comes from the Jacobian of the transformation. Yeah. Okay. So, where r and theta exist within the xy plane, and dz is just going up and down. So the triple integral of this guy okay, so d theta is my outmost term. Okay? And so when I look at this cylinder that I'm talking about, actually I'm going to move the cylinder on top of this while I do this. No, that's not going to work. I'll just have to move that down. Okay, so let's say we had d theta as our outmost term. And so it's a full rotation. So the full rotation of that circle within the xy plane would be 0 to 2 pi. Okay. Now my dz would go from 0 to 3, and my radius, which is the innermost term, would go from 0 to 2. And, well, x squared, this would be r squared cosine squared of theta, r squared sine squared of theta, and then plus z squared, because z doesn't get changed, and then r, dr, dz, d theta. Okay, so that's my transformation into the cylindrical coordinate systems. Okay. And remember, cosine squared plus sine squared equals 1. So what is this first term right here? It's really just r squared. And so that would equal the integral from 0 to 2 pi, the integral from 0 to 3, the integral from 0 to 2, of then r squared plus z squared, and then r dr dz theta. Okay, let's go ahead and distribute that, the extra r inside there, and we can integrate. Okay. So that becomes the integral from 0 to 2 pi. The integral from 0 to 3, integral from 0 to 2, of now r cubed plus z squared times r, dr, dz, d theta. That becomes the integral from 0 to 2 pi. The integral from 0 to 3. So r cubed becomes r to the 4th divided by 4. And then plus z squared, now r squared, divided by 2. Both of these will be evaluated at 0 and 2. And we did the integration with respect to r, so now this becomes dz d theta. Okay, now r to the, we don't care about the zero term, but r to the fourth divided by 4, evaluated at 2, what does that become? That becomes a 4. So it becomes the integral from 0 to 2 pi, the integral from 0 to 3. Okay, so this term just becomes a 4. And then this, if I square 2, that's a 4. 4 divided by 2 is 2, so that's going to be z squared times 2, and then dz d theta. Okay, now we're integrating with respect to z. So, this becomes the integral from 0 to 2 pi. That's going to be 4z plus z cubed divided by 3 multiplied by 2, evaluated at 0 and 3, d theta. Okay, so now, but once again, we don't care about the 0 term. But when we plug 3 into this thing, well, 4 times 3 is going to be 12. And then z cubed divided by 3, that, that becomes 3 cubed divided by 3, which is 3 squared, which is 9, and then 9 times 2 is 18. So that becomes the integral from 0 to 2 pi of 12 plus 18 d theta, which equals the integral from 0 to 2 pi of just 30 d theta, which equals 30 theta, 30 theta, evaluated at 0 and at 2 pi. And so, and the answer ends up being 60 pi. Okay, so that's the outward flux along the vector field. In cylindrical coordinate systems.